Assalamualaikum and salam sejahtera to all fellow researchers. I'm Noor Fadzilah binti Ismail and will present my progress research work titled Characterization of Simple Nanoparticle Porous Silicon-Based Substrate for Detection of Low Concentration Dengue NS1 Protein. Dengue is a major international public health issue since 2015. In Malaysia, annually approximated more than 100,000 cases with roughly 200 fatal cases are reported. Early detection of the infection during the first few days is important for monitoring the patient health condition with the disease and help in reducing the fatality rate. Recently, dengue virus non-structural 1 or NS1 protein has been accepted as an early biomarker for dengue infection. Currently, the presence of NS1 is detected through enzyme-linked immunosorbent assay (ELISA) and immunochromatography (ICT) rapid test kit. Both tests require patient blood, which is invasive and prone to blood infection risk. However, the presence of NS1 protein in saliva is far less in concentration than in blood, making more challenging. In this study, surface enhancement Raman spectroscopy (CEEES) proposed as a suitable method to detect low concentration NS1 in saliva. This sensitive and specific technique. The performance is highly dependent on the substrate used. Such substrate is the nanostructured noble metal which is adsorbed to the analytes that amplifies Raman scattering. The focus of this study is to fabricate the optimum substrate for detection of low concentration NS1. The electrochemical etching technique is employed to fabricate porous silicon with variation in structural features serve as the substrate base. The main porous silicon features is the high surface area. This is performed due to the etching process of the silicon surface that produces the roughness surface which can increase the Raman intensity. Thus, the advantage of porous silicon structure is the enhancement of the Raman intensity. The porous silicon structure surface will be coated with different sizes of silver nanoparticle. The silver Ag is found to be capable of enhancing the Raman intensity of various molecules. Silver nanoparticles also act as shielding layer and provide long-term stability for the substrate layer. Then, the surface characterization of the sample is investigated through the field emission scanning electron microscope or FESAM to find the optimal size of porous silicon structure performance. And finally, the substrate with the optimal size of silver nanoparticle will be functionalized with dengue NS1 antibody, and the performance will be evaluated based on enhancement factor and limit of detection. The Raman characterization of the sample will be performed by evaluating the Raman signal of the substrate. It is expected that the intensity of the NS1 protein Raman spectrum at low concentration will be significantly amplified to a detectable range, enabling dengue virus NS1 detection in saliva. Figure 1 presents the conceptual model of dengue virus NS1 protein substrate. The substrate is the illustration of porous silicon that being layered with silver nanoparticles. This is the current status of my research work based on the research activity and data collection that being planned through the semester. The data collection for structural, electrical, Raman characterizations, and performance evaluation for detection low concentration of NS1 to achieve first, second, and third objective is fully done. The document preparation for thesis is still in progress. I will wrap up all the research work as soon as possible after finish reviewing my thesis with my supervisor. Dengue virus NS1 protein is accepted as early biomarker for detection of dengue infection. Here are the problem statements stated for this research. The current detection of dengue virus on S1 method use a blood sample, which is invasive and prone to infection. Examples of the method are ELISA and rapid test kit. Besides the use of saliva, had been attempt reported in the literature, such as K.L. Anders et al. Used ELISA with a reported sensitivity of 64.7%, while Mercado et al. Used rapid tests and concluded that NS1 in saliva was undetectable, even in acute cases. Other than that, by using sense and signal processing technique, Rathod et al. Reported the sensitivity of more than 80% while using commercially available substrate. The commercially available substrate used in the study is gold-coated slide. For cells to be accepted as early and non-invasive screening or diagnostic technique for dengue, better performance should be achieved. Thus, better cell substrate for detection of NS1 protein at low concentration is in need. The better performance depends on the structure physically and chemically. The cell substrate should form good analytic feature in terms of surface enhancement factor, reproducibility, uniformity, and unit of detection. First objective is to fabricate silver nanoparticle coated porosilicon cell substrate using electrochemical technique. The second objective is to characterize the silver nanoparticle coated porosilicon cell substrate in terms of electrical and Raman properties. The third objective is to evaluate the performance of silver nanoparticle coated porosilicon cell substrate in detecting low concentration dengue NS1. Figure 2 shows the porosilicon structure formation. It is developed in the first stage of fabrication method. In order to enhance the Raman scattering, the DCPEC technique reported in NSM Razali paper seems suitable to apply in this experiment because of the small sample instrument production with affordable cost. Etching time duration, current density duration, and size of silver nanoparticles are the parameters taking place in the fabrication process. The effect of the parameters application for porosilicon produced are analyzed using structural and electrical characterization. Figure 3 illustrates the FISM characterization of porosilicon cell substrate for etching time of 20 minutes from the top view. The cross shape with macroporous size is formed. Figure 4 illustrates the FISM characterization from the cross-section view. The V-shaped porosilicon is formed. Figure 5 depicts FISM characterization of porosilicon cell substrate for current density of 20 mA per cm squared from top view, while Figure 6 depicts FISM of characterization from cross-section view. Figure 7 depicts FISM characterization of porosilicon cell substrate coated with silver nanoparticle from top view. The electrical characterization is one of the aspects that need consideration in the porosilicon structure delay development. The effect after turning the variable shows the electrical behavior of the substrate development. Figure 9a shows IV curve graph of the different silicon structure which are bare silicon, porosilicon, and porosilicon coated with silver nanoparticle. Figure 9b shows the IV curve graph of the porosilicon sample at different duration of etching time. Figure 9c shows the sensitivity property of the porosilicon structure with different etching time setting. The sensitivity values are extracted from IV curve at 10-fold for every sample. The slope is calculated from the best fit line through all the etching time samples. The graph shows sensitivity for all samples increasing linearly with etching time. To evaluate the limit of detection of R6G, several concentrations are deposited on the cell substrate, such as 1, 0.1 and 0.01 mg per milliliter. Figure 14 depicts the signature peaks of R6G at 611, 711, 1183, 1310, 1360, and 1507 per centimeter are obvious on 1 and 0.1 mg per milliliter concentration of R6G. However, as the concentration reduced to 0.01 mg per milliliter, the signature peaks are noted but scarce. The presence of the peak might not be visible if concentration is reduced further. Thus, the limit of detection for R6G is set at 0.01 mg per milliliter. For NS1 detection, the best porous silicon cell substrate coated with silver nanoparticle sample tested with 0.01 mg per milliliter deposit on different functionalized substrate, such as porous silicon with silver nanoparticle, porous silicon without silver nanoparticle, and bare silicon without silver nanoparticle. From this research work, it is shown that dengue virus NS1 is Raman active at Raman peak of 5 to 0 per centimeter. Figure 15 illustrates Raman spectra of functionalized silver nanoparticle coated porous silicon acquired from two samples, S1 and S2, taken at different spots. This figure shows the Raman spectra acquired from these two samples of functionalized silver nanoparticle coated porous silicon substrate. Several peaks are observed and labeled. The appearance of the peaks are consistent in every spectrum. Confirming peaks related to the substrate is important prior to detection of low concentration NS1 in order to ensure the detected peak originated from the NS1 molecule and not from the substrate. The performance of the designed silver nanoparticles porous silicon substrate illustrated in figure 16, where the Raman spectra of NS1 0.01 mg per milliliter deposit on different samples, which is black spectra indicates functionalized porous silicon with silver nanoparticle. The red spectra indicate the functionalized porous silicon without silver nanoparticle, and blue spectra indicates functionalized bare silicon without silver nanoparticles. No additional peaks are observed on the functionalized porous silicon and bare silicon. The only significant peaks observed is 5 to 0%, corresponding to the silicon crystalline structure. This indicates that these two substrates are unable to detect the presence of NS1 at 0.01 mg per milliliter. However, note that peak intensity of 5 to 0% obtained from functionalized porous silicon substrate has a significantly higher intensity than bare silicon substrate. This shows that the form microstructure have improved the occurrence of Raman scattering in the vicinity of the substrate surface. The amplification is expected owing to successive scattering experienced by trapped photons entering the porous structure. Porous silicon coated with silver nanoparticle has produced Raman spectrums for additional significant peaks. Figure 17 illustrates the Raman spectrum obtained from 0.1, 0.05, 0.02, and 0.01 mg per milliliter of NS1. Figure 18 shows the Raman spectra of NS1 for much lower concentration, such as 0.05, 0.02, and 0.01 mg per milliliter. Raman spectrum of the substrate without NS1 is also included to differentiate between peak associated with the substrate or NS1. With referring to the NS1 at 0.01 mg per milliliter spectrum, several very weak peaks are observed at Raman peak, such as 684, 934, 1138, 1340, and 1535. Comparing figure 15 and figure 16 before, Raman peak at 934% is belong to the substrate, while peaks at 683, 1384, and 1535% also present in NS1 Raman spectrum at 0.01 mg per milliliter, present in this figure 17. Hence, the fabricated functionalized silver nanoparticle coated porosilicon substrate can detect the presence of NS1 up to 0.01 mg per milliliter. But the result obtained may not necessarily be impressive, but can be considered promising for NS1 detection. This is the current status of my research work based on the objective achievement. The data analysis to achieve first objective is successfully done with the performance comparison between the etching time duration were able to analyze. Meanwhile, for parameter of varying current density doesn't give any significant difference. Only the varying etching time is decided to be proceed for the next data collection. The data analysis to achieve second objective is successfully done by electrical characterization observation and select the 3 samples that gave highest current value. The Raman spectrum and enhancement factor being observed. Sample of the cell substrate with etching time of 22 minutes coated with 75 nanometer silver nanoparticle size produce the highest peak of Raman intensity and will increase the enhancement factor. The data analysis to achieve the objective is successfully complete by surface functionalization process. The sample surface functionalized with antibody and dengue virus NS1 at lowest concentration of 0.01 mg per milliliter is analyzed on different functionalized substrate. The list of publications for this research work is as below. There are 4 publications that are accepted, and also some of it is published in conference paper and journals article respectively. We also have this ongoing paper which is aimed as journal publication. This is percentage of completion of each chapter for thesis writing. Overall percentage is estimated about 70 to 80% for now. What's left in my list is to successfully finish my thesis writing. That's all from me. Thank you.